Here we are at lecture 1C, density of gases, and this will be an even shorter discussion here. Just a couple of slides on something we don't always think of, the density of gases. We're going to look at a little bit of a derivation on how we get to an equation using the ideal gas law to determine the density of a gas. Now, if you remember when we were talking about density many courses ago, or one course ago, we said density is equal to mass over volume. Very common equation. I've studied many times in earlier classes, even in high school. Now, we also learned in our introductory chemistry course that the number of moles is equal to mass over molar mass. We take grams, divide by molar mass of a compound, and that gives us the number of moles. Fairly straightforward. Now, the reason we want to do this is because it does give us a mass term that we're looking for in density. Because if we want to calculate density, we need mass and we need volume. And we don't often look at necessarily the mass of a gas in that sense, and we don't have the term mass in our ideal gas law. Now, our ideal gas law is PV is equal to nRT, as we saw just in the previous lecture. Well, what we can do here is we can take our expression for N and substitute it in there into our ideal gas law. And what we end up with is an equation here. So P times V is equal to M over molar mass times RT. Well, notice now in our ideal gas law that we have the term M for mass and we've got the term V for volume. And so we have the two variables needed in order to express density. And so if we rearrange this equation so that we have M over V on one side of the equation and all the other variables on the other side of the equation, we can get a phrase for density. And so that we have density is equal to mass over volume. So it's equal to pressure times the molar mass divided by RT. And now we have an expression for density for an ideal gas. We can rearrange that into something that actually looks an awful lot like the ideal gas law, but is not. But it's pressure times molar mass is equal to density times R times T. So one of the things that tells us is that density is impacted by the molar mass of the gas, the pressure that the gas is under, and the temperature of the gas. So if we take a look at an example, we want to know what's the density of xenon hexafluoride gas at STP. We have our equation that we just learned. P molar mass is equal to density RT. We put in our value for pressure, 1 bar, because we know we're at STP. We look up the molar mass of xenon hexafluoride and we get 245.3 grams per mole. That's going to be equal to our density that we don't know. It's our variable that we don't know, times R, 0.08314 liter bar per Kelvin mole, times our temperature. And again, our temperature at STP is 273 Kelvin. Well, we can see that what we're going to end up with for units is our bars are going to cancel, our kelvins are going to cancel, and our moles are going to cancel. And we're going to be left with 2 units, grams and liters. And what we end up with a value is 10.81 grams per liter. Now, when we're looking at normal materials, solids and liquids, normally we express our density in terms of grams per milliliter. And you can do that for a gas as well. However, that does tend to lead to very small values with negative exponents. And so it's more traditional to express densities of gases in grams per liter.